Bismillah ar-Rahman ar-Rahim. In this example, we want to verify the Stokes theorem of a vector field that's given in the cylindrical coordinates r hat r cosine phi plus phi hat sine phi for the path shown in the figure, where it looks like it's part of a circle or a washer, if you like, where r is varying from 2 to 5 and phi is varying from 30 to 50, and this is in the xy plane, so z hat in this case is equal to 0. So again, Stokes' theorem states that the circulation, which is the line integral of b dot dl, is equal to the surface, this is the contour integral of the surface integral of the curl of B. And this is with respect to ds. So let me start with the left hand side and do this line integration. Oh, let me put this, let's say, in blue. So as we can see here, there are 4 line segments and they are different from each other, so we should calculate four different integral and sum them up together. So this is equal to the integration from a to b of b dot dl plus the integration from b to c of b dot dl, integration of c to d, where d is over here, of b dot dl plus the integration from d to a of b dot dl. Okay, and the integration is, this is b. So first of all, we need to figure out what is dl in cylindrical coordinates, and we can pull this from the formula sheet. And doing so, we will find that dl is equal to r hat dr plus theta hat or phi hat r d phi plus z hat dz. And doing so now, b, let me write what b is so that it's be more convenient to us. So b is equal to r hat r cosine phi plus phi hat sine phi. So let me just grab this down. You're gonna put it here. So I copied here the figure for convenience, and as we did already, we will have only the common elements, because when we do the dot product, this dot product I'm talking about, we will have 0 for perpendicular elements. So what I'm saying is that for the segment a to b, so for this segment a to b, we will have r cosine phi and this is dr, and then we will have from A to B r sine phi d phi. So this is for the first integration. Let me do the integration separately. So as we are going from A to B, we can see here that r is constant, it's equal to 2. So dr is from 2 to 2, from 2 to 2. And phi is varying in this case from 60 to 30. And this 60 to 30 defines the angle as the direction as well. So if you do the limits like this, you don't need to take care of the cosine theta for the dot product. So this is of course 0. And there is a plus sign in here. And r is constant, it's equal to 2. The integration of sine is minus cosine, so this is minus. And here I have cosine phi. And you should convert excuse me, convert the angles to radian, but since I'm only calculating this inside the cosine and the sine, it will not make any difference. So this is integrated from 0 to 6, from 60 to 30. So this is minus 2 times cosine 30 is square root of 3 over 2, and cosine 60 is 1 over 2. So 2 will cancel out, and I will have, because I have the minus sign here, it will be 1 minus square root of 3. So this is for the segment A to B. Now for the segment B to C, B dot dl. In this case, well, the dot product is going to be exactly the same, but the limits of the integration for the first integral is going to be from 5 to 5, and the angle is exactly the same, so this is going to be 0. So let me just write this down. dr, this is equal to 0, and this is now, no, we're doing BC, I'm sorry, BC. When you do the dot product, is going to be the same, yes, but the integration is going to be from point B to point C, so this is from 2 to 5, because here r is equal to 2 and here r is equal to 5. So this is for r cosine phi dr plus, and this integration. Now for the line BC, the angle is constant, so this is from 30 to 30, and this is r sine phi d phi, and this is equal to 0. So this is simply now phi in this case is constant and it's equal to 30. So phi is equal to 30 degrees. So cosine 30 is square root of 3 over 2. And the integration of r is r square over 2. And you're integrating this from 2 to 5. So this means that I have square root of 3 over 4, and this is multiplied by 25 minus 4, and 25 minus 4 is 21, so I have 21 square root of 3 over 4. Now for the segment C to D, that's this segment over here from C to D, the 5 here is equal to, or r is equal to 5, it's constant, so for the first integral it is, the limits are 5 to 5, and for the second integral the limits are 30 to 60, because at C phi is equal to 30 and at D z phi is equal to 60. So if you compute the integration, you will find the result 5 over 2 multiplied by 1 minus square root of 3. Now for the last integration, the limits are d to a of b dot dl, and in this case r is varying from 5 to 2, and this is r cosine phi dr, and in this case phi is constant, is equal to 60, so this is from 60 to 60, and the integrand here is r sine phi d phi. This is of course equal to 0 because the limits are the same. And for this one I have cosine phi. Now in this case phi is equal to 60 degrees, so cosine phi is constant and it's equal to 1 over 2, and I'm integrating, or r dr, and this is r square over 2, and the limits are from 5 to 2. So in this case from 5 to 2, and in this case I have 1 over 2 times 1 over 2 minus 25 over 2 and in this case, okay, I have minus 24 over 4. Now these are the line integrations along the path. Now what I will have to do is to sum them all up to calculate the overall line integration. So the circulation in this case, which is integration of b dot dl over the contour, is equal to 1 minus square root of 3 plus 21 square root of 3 over 4 plus, I'm going to distribute the multiplication over the addition here, 5 over 2 minus 5 over 2 square root of 3 minus 24 over 4. And I just realized I did a little mistake in here. I forgot this minus sign, so this should be square root of 3 minus 1, and when doing this I will have minus 5 over 2 plus 5 over 2 square root of 3. So doing the math, this one is 4 over, or 2 over 2, so 2 over 2 minus 5 over 2 is minus 3 over 2, minus 24 over 4 is minus 27 over 4. And for the square root of 3, it will be multiplied by, here I have minus 4. Minus 4 plus 21 is plus 17, and plus 17 plus 10 is 27 over 4. So I have plus 27 over 4 square root of 3. And if you take 27 over 4 the common factor, you will get 27 over 4 multiplied by square root of 3 minus 1. Now all of this was for the left hand side. For the right hand side, I know that this should equal to the surface integral of B, of the curl of B dot ds. And for that I need first to calculate the curl of B. And I need to use the formula for the cylindrical coordinates. And going back to the formula sheet or the book, you can find that this is equal to this. And to do so, let me just grab this down a bit like this. Now I just need to substitute the values of B, and this is now my the equation of the vector field, so I just need to substitute the values. So I'm going to have r hat partial over partial r, and the component along the r hat direction is r cosine phi. Along phi hat, the component along phi hat is phi hat, sorry, no phi hat, is simply sine phi, but I need to multiply this by r because I have r here in the formula. And then finally for the z hat direction, there's a partial in here, partial over partial z, and az is equal to 0. So computing the determinant, I have r hat multiplied by, this should be minus the derivative of this with respect to z, but well, this is 0, so I will not have any r hat component because it will be 0 minus 0. So 0 r hat, or r hat times 0, and then for the phi hat, don't forget the r in here, so that's phi hat r, and phi hat r is going to multiplied by the partial derivative of 0, that's 0, and this is the derivative of this component with respect to z, which is also equal to 0. And this kind of makes sense because the vector field is in the r phi plane, and we know that the curl should be in the normal direction of the, or normal to the vector field. So anyways, this is r and this is the component along phi, and for the component along z I will have plus z hat, and this will be multiplied by, I'm going to take the derivative of r sine theta with respect to r. I have only r constant, so this is sine phi, and this is minus the derivative of this with respect to phi. The derivative of r cosine phi is minus r sine phi, so this is going to be minus times minus, so this is plus r sine phi. Okay, now I calculate the integration, the surface integration. But to do this, I need to find ds. What is ds that I should use? So I need to calculate the integration of the curl, the surface integration of the curl, and this is dot ds vector. And in our case, z is constant because z is equal to 0 all the time, because this is only the y or the xy plane. So z is constant, and it's equal to 0. And we know that the ds should be the one that's normal to the surface. So this is another way to see this. If this is my three-dimensional space and my washer looks more like, or my slice of a washer looks more or less something like this, dsz should be normal to this. So this is dsz. So this will be notated as dsz in your formula sheet. So let's see how much is this equal to. So according to the book, this is my dsz. I'm just going to rewrite it here, or just write it explicitly in here. So this is now the integration. Now if I remove this circle, I'm going to have double integration. These are with respect to dr and d phi. The curl has only a z hat component, so this is z hat sine phi plus r sine phi, and I need to calculate the dot product of this with respect to dsz, but dsz is z hat r dr d phi. Okay, so z hat times z hat is equal to, I'm just going to write this, and r in this case is varying from 2 to 5, and phi is varying from 30 to 60. Now pay attention that if I'm having something like phi over here that's not inside the sine or the cosine, then I need to convert the 30 and 60 to phi. But since this is not the case, this is not necessary. So now I'm going to compute this. This integration of this with respect to, oh, I have an r in here, so this is r sine phi. So r, integration of r is r square over 2, and this should be integrated. You need to be careful with your integration to get it right. And sine phi, integration of sine phi is minus cosine phi, and this is going to be integrated from 30 to 60, and then I have plus sign, and this is now r square because I have r outside in there, so this is r square over 2. When you integrate this, it will be r cube over 3, and this is again integrated from 2 to 5, and this is minus cosine phi, and this is integrated from 30 to 60. And I just realized that I forgot this 1 over r in here. So this whole thing is multiplied by 1 over r. And this will change some things in here. So this will be sine over r. And this will be, well, r will cancel with r, and then I will have nothing in here. Now, since we got confused already, let me just write this explicitly, how it looks like. This is equal to, so this is now equal to equal to the double integral from 30 to 60 and from 2 to 5. And here z hat will cancel out, this will not change, but here I have sine phi plus r sine phi. Let's take sine phi as a common factor to make it easier. Sine phi multiplied by 1 plus r dr d phi. So now, since they are multiplied, this function is a multiple of two functions that one of them is a function of phi only and the other one is a function of r only, I'm allowed to do this. I'm allowed to integrate each one of them separately and then multiply the results by each other. So the integration of sine is minus cosine phi, and this is integrated from 30 to 60, and the integration of this is r plus r squared over 2, and this is from 2 to 5. And if you like, I can, if I take 1 over 2 here outside, then I will have here 2r plus r squared. This should be the same function. Now when you substitute, this is 1 over 2. I'm going to take the minus outside. Cosine 30 is 1 over 2, and sine 30 is square root of 3 over 2. And this should be 2. 5 minus 3 is, minus 2 is 3, plus, and this should be 25 minus 4, which is 21. 25 minus 4, yes, that's right. So doing the mathematics, this should be minus 1 over 2. Well, I'm going to take 1 over 2 as a common factor here, so this is minus 1 over 4. And this is 1 minus square root of 3. And this is simply 27. Okay, so this is equal to 27 over 4 times the square root of 3 minus 1. And we notice that this is the same result as before. 27 over 4 square root of 3 minus 1. 27, not 24. 27 over 4 times square root of 3 minus 1. So this is correct, and hence the Stokes theorem is verified. Thanks for watching, and I will see if I can record more video tutorials on this topic.